We're alive. Okay. So fun with fractions. Addition. And then the addition will lead us into subtraction. So just the basic idea, whenever we model something, we have to come up with explanations for two things in our model, some concrete thing. For example, one is, what do the numbers look like? And two, what does it mean to do the operation? By operation, I mean addition or subtraction or multiplication and division. And operate only has one key. So for us, a fraction is equal part of a whole. Could be parts. And for addition, it just means combine and count. And so when we first start off and we do something like 1/3 plus 1/4, we have to come up with a concrete model for what does it mean to be equal parts of a whole today. And drawing-wise, the easiest thing to do, in my opinion, is to just draw as equal as possible these square cakes. And then just to slice them up with lines. When I do that, I usually slice one of them vertically and the other one horizontally. So maybe this one over here is my 1/3, and let's say that one right there is my 1/4. So we can only combine and count like things. And although these are both pieces of cakes, they're different sizes, so that's a problem. So the trick is to cut each cake like the other. So the thirds cake I cut in fourths. And this is where the cutting in the different directions can come in handy. And the fourths cake I cut in 2/3. So you're going to be doing this in 3rd, 4th grade, getting it started. How many kids, are most of the kids going to be able to draw this well enough, do you think? There's going to be some that are going to really struggle to draw it, right? So the toys are nice in that regard because then everybody has the same thing to play with. So if drawing is hard for enough of your kids, then acquiring a set of pattern blocks is a good idea, okay? And you can't do every fraction with pattern blocks, so you have to be selective. For example, if that's my whole, I can talk about halves, right? I can talk about thirds, and I can talk about sixths, if that's my whole right there. And so the toys kind of limit what kind of fractions you can work with. And that's fine, you don't need to hit every example, because this is kind of just building visions in their head about how all this fits together. If the toys aren't available and drawing is a problem, paper folding is another great thing you can do. So just imagine this right here. Instead of me drawing this on a piece of paper, I actually take a piece of paper and I fold one piece of paper in thirds. So you try to show the kids tricks for folding into thirds. And anybody know a trick for folding into thirds, piece of paper? Like you ever fold letters into thirds to mail them?
Oh, yeah.
Where you fold one side down and you kind of guide the other to kind of match up best you can. It doesn't have to be perfect, but just close enough. Quarters aren't bad, right? You go half and then half again. So you can pick the fractions that you add carefully so that you can easily fold to make that happen. Maybe too many kids are having trouble doing thirds, and if you can't have an aid help you, just don't do thirds then. Do something else. Do quarters and halves, for example. But there's a lot of different things you can play around with to get this good. All right, so whether we draw or fold paper, we have now equal size pieces. So each of the pieces I have here, 4 of them there and 3 of them there, they're exactly the same size. So the next thing we do is we make a note of, okay, what's the new name for 1/3 based on this picture? It'd be 4 out of 12, because we know this is 3 by 4, so we've got 4 12ths instead of 1/3. And the new name for the fourths would be 3 12ths. So now we can easily count them. How many equal sized pieces do I have? 7. Yeah, 7 when we put them all together. And they are 12ths. And it's always a good idea to then redraw that new amount. So I have thirds coming this way, I have quarters going that way, and then I'm just going to fill in originally my 1, 2, 3, 4 pieces, and then 1, 2, 3 more. And often I try to look at a way, can I regroup them to simplify this? And I think kids will realize pretty quick that 7 and 12 have no common divisors, so I can't reduce it. I can't get groups of 2 here, I can't get groups of 3 without having 1 left over, so we're stuck. It's just 7 12ths. So you spend a lot of time over and over again drawing these pictures, making the models, getting kids just used to these really simple ones. However, eventually we're going to get problems that we can't draw pictures of easily. So I'm just going to bring up another example. So let's see. Somebody give me a prime number.
7.
7. Okay. I'm going to double that. Oops. That's not 10. I'm going to double that and make it 14. Somebody give me a different prime number. 11. And I'm going to double that and make it 22. Next thing I'm going to do is pick 2 numerators so that the fractions don't reduce. So what would a numerator I could put up here so that the fraction won't reduce? How many 14ths should we have? Like I wouldn't want to pick 7 14ths because that would reduce to 1/2.
3.
3 would work? Yeah. Okay. And how many 22nds should we have so it doesn't reduce? 5. Excellent. Would you agree none of us really want to draw that picture as a cake? And our toys aren't going to be able to draw that picture. So ultimately, we have to move beyond a model and we need an algorithm. So what I'd like you to do now is apply your favorite fraction addition algorithm and come up with an answer. So I have one version of an algorithm called the LCD algorithm here. Compare to mine once you get yours done. I didn't make any arithmetic mistakes. I think I have an answer. I'm going to do it a different way in just a moment. Compare. All right, let's take a look at this together. So I'm just going to explain what I did, and I'm going to write down some steps as I go. So with the LCD algorithm, if you don't have a common denominator, then you have to find one, and LCD stands for lowest common denominator. Which is the lowest common multiple of the denominators. So step one would be to factor each denominator. So that's what I did first right here. So I factored 14 as 2 times 7, so I used our factor tree method. I factored 22 as 2 times 11. Then I had to look at those to determine the lowest common multiple. So 2, find the lowest common multiple. So I determined there that the LCM should have a 2 times 7 in it, and then 22 says it better have an 11 in there too. Multiplying 2 times 7 times 11, if I didn't make a mistake, I got 154. Anyone else get 154? All right, now he's completed that. Once I have that, I have to then figure out how to adjust each fraction, right? So then I have to back up. Say, all right, step 3, I basically have to divide a denominator into that LCM to find the missing factor. For each fraction. So that's 2 different steps. So you have to do it for the first denominator. So 14 goes into 154. How many times? 11 times. Now, kind of a cheat sheet on that can be really nice is if you factor the denominators in place, 2 times 7, 2 times 11, and you list the factors of the LCM, then you can just compare the factors here to the factors there and say, oh, this guy's missing an 11. 2, 11, this one's missing the 7. Okay, so that can make it a little bit easier. That kind of takes half the step out of that one right there. because I need 154, which is 2 times 7 times 11. So then we multiply top and bottom by that. So that's like another step. Multiply the numerator and the denominator by that missing factor. For each fraction. This is complicated, isn't it? I wonder if people don't like adding fractions. And then we clean that up to get the new fractions. Okay, so we're 2/3 of the way done with this algorithm. So I've gotten to this step right here, and then I clean them up to get each new fraction. So now that I have a common denominator, I can add the numerators. But then I have to see if it reduces. So step 5, add numerators. We write that over common denominator. And then step 6 would be to reduce if possible. This is, again, known as the LCD algorithm for adding fractions. Same process for subtracting. Instead of adding the numerators, we subtract them. So that's kind of nice. Once you learn how to add, you know how to subtract fractions. Now, just something to point out, even though we found the lowest possible denominator, you cannot do this with a smaller number than 154. I still had to reduce. Do you always have to reduce? No, sometimes it doesn't, sometimes it does. Kind of depends on two things. It depends on your denominators and it depends on your numerators. It's complicated. There's no simple answer there. Once upon a time, I thought there was a simple answer about when it would reduce and when it wouldn't. And after studying it for on average an hour or two a night for 3 months, I determined there was no easy answer. So, it's one of those problems where it's like, oh man, I hope it seems like there should be an easy one, but there's not. I learned a lot. Just didn't come up with an easy answer. So let's look at it a slightly different way. So I have an answer. We'll just start over. So new page here. So oops, wrong button. That one. There we go. So we've got 3 14ths, and we want to add that to 5 22nds. So an alternative algorithm is to not worry about finding the lowest common denominator. Just say, I just need a denominator. The quickest way to get a denominator is just multiply those two together. So what is 22 times 14?
308.
Okay. Everything tells me it's 308. Take a word.
Not 100% sure.
I think you're right. If I double 154, I get that. And I was thinking that if I double 14, I get 28. 28 plus 280 is 308. Yeah, it is definitely 208. Then all I need to do, since I multiplied 14 by 22, I better multiply the 3 times 22. That's not too bad. 3 times 22, I can pretty quickly see is 66. 14 times 5, I got to think a little harder. That's 50 and 20, which I think is 70. So my numerator is now 60 plus 70, which is 136. That was way easier, wasn't it? Okay, but I got to reduce it. Okay, what do you think it reduces by first? 2, yeah. So we cut the top and the bottom in half. And whether we use a calculator or scribble that on a piece of paper, half of 136 is going to be 50 and
It's 68.
68. Okay. And half of 208 is
It'll be-
104.
It's 308.
Oh, it's 308. Yes, not 208 terms. That's going to be harder to split. How about 154? Does it still reduce?
Yes.
Yeah, so I reduce again. So I'm just going to make a note. It's always a good idea to write. I divided that by 2 and I divided that by 2. Doing that again. Divide by 2, divide by 2, 34, and 77. Okay. So the question is, what's harder? Is reducing harder, or is finding the LCM and adjusting each fraction harder? What's that?
I think the LCM.
I personally think the LCM is harder to find and work with than it is to reduce. But some people, yeah, it depends on the person, it depends on their experience. I think kids are a little blanker slate than us, and so we might have better luck with kids using this method right here. I call it the Arawa algorithm. If this is in our textbook, if you look it up in the textbook, they just call it the definition of fraction addition.
Thank you.
And it's my preference. So in addition to teaching this class, I teach algebra and sometimes arithmetic for GED students. And generally, people really struggle with fraction addition. And I show them the arrow method, and that kind of like opens up a door for them to walk through with a little more confidence that they can deal with fractions, because addition and subtraction are the hardest things. But bottom line is, in most textbooks, ultimately kids are going to need to know the lowest common denominator method. And it turns out in algebra, so in algebra classes, we teach things like what is 2x over x plus 1 plus x minus 7 over x squared plus 2x plus 3. And we got to find a common denominator there. And it turns out the Arawa algorithm is actually a detriment here, and the LCD algorithm is the way to go once you have variables in there. So ultimately, if kids are going to go on into science-type fields, they really need to know the LCD algorithm. So I'm not saying you shouldn't teach it. It will be in the curriculum, but more and more often now, you will see alternative algorithms in traditional curriculum. And so I guarantee you'll see both methods these days. As far as the book's reference to this as the definition of fraction addition, I'll just present it the way it is there, because I do want to just touch on variables a little bit here. So they say if you have a fraction, a over b, and you add that to another fraction, c over d, the sum is always equal to a denominator of BD and a numerator of AD plus BC. And the book just states that. They say, here's the definition. But if you imagine the arrows sitting on top of this, there's your BD, here's your AD, and here's your BC. Anytime the denominators have no common factors, the LCD algorithm and the Arawa algorithm are identical. So, for example, earlier we had 1/3 and 1/4, and the LCD of 3 and 4, the lowest common multiple of 3 and 4, is 12. And the Arawa algorithm also says to use 12. So sometimes they're one and the same, sometimes they're not. So let's do another example. Let's take, and then we'll throw some variables in. So somebody give me a prime number. Or forget about prime number. Give me an odd number.
17.
17. Okay. Sure. Now another odd number.
31.
31. Oh man, you guys are making life hard here. Okay. So then we'll pick numerators so these won't reduce, which is pretty easy because they're both prime, which means just about any proper fraction will work here. So maybe we'll have 5/17 and 6/31. Since 17 and 31 are prime, the Arawa algorithm is the way to go here because it's the same as the LCD algorithm. But the problem is, if you're thinking LCD, you have to work to prove that they're prime first. That the only possible common, the smallest common multiple is 17 times 31. Okay. So if you're always thinking LCD algorithm, then you have to work hard to determine, you just multiply those two together. All right, add these, see what you get. We'll compare notes. Oops, it's down wrong. That digit's in the wrong order. I think I have an answer. Hopefully somebody else got one that matches.
I think it's 257. I want to say this.
The numerator?
Yeah.
All right,
I think about the same too.
so 31 times 5, 5 times 1 is 5, 5 times 2 is 15, and 17 times 6. 7 times 6 is, oh, it's 42, not 43, right? So that should be 1 and 2. Thank you. Algorithms are trying to do it in my head. So that's a 2, and then this is a 7. All right, now we're doing better. So this was a hard problem. Does it reduce? Oh my gosh.
Yes.
It does?
Yes.
By what?
3.
5, 6, 7.
Wait, never mind. No, I'm wrong. Ignore me. I was saying the wrong thing.
So just to check on the reducing, I know that 17 is prime and 31 is prime. Okay, so I had to think about that in my head for a while. That means 527 is literally just 17 times 31. So the only way this is going to reduce is if 17 goes into the numerator or if 31 goes into the numerator. And so I could just check those two, and it turns out it can't happen. It's not obvious that it can't happen, but it can. So if you just check that, you'll find out. So I'm just going to give you a couple of tricks that are helpful for, because sometimes in class you have tons of problems from whatever book you're using, and you can just look in there and get a new problem, and look in there and get a new problem. But other times in class on the fly, all of a sudden you need a new problem that meets certain ideas. So notice this time I asked for prime numbers, and the answer did not reduce. Do you remember what I did last time I asked for prime numbers after you guys gave me prime numbers?
You doubled them.
I doubled them. So it turns out if you start off with prime numbers, but then you double them, you will always reduce. And I mentioned I spent months thinking about this problem, and it wasn't just because I was bored and I was thinking about it. It came up for a good reason. So we use online homework system. You guys get to use them, right? And somebody said on a test, when the computer generates a pair of fractions for somebody to add, your pair of fractions might simplify after, but yours wouldn't. And that seemed totally unfair. So somebody asked me, can you come up with a way to pick fractions so that you're guaranteed it always reduces, or you're guaranteed it never reduces, for fairness when we're generating problems for tests. And so a friend of mine and I studied this for a while, and we were able to figure out when you can reduce, when you can't reduce, and then there's all these beautiful fuzzy cases in the middle that it's kind of rough. But the simplest version is, I'll put this at the end. So this is just, it's not in the book, it's just a cool fact about fractionalization. So cool fact. If you have a prime number in the denominator, and there's a trickier case of this, so I'm going to go over the simple version. And if you have a different prime number for this denominator, and then you pick numerators so that these don't reduce, I should say can't reduce. Can't reduce. Then when you add these guys together, the sum will never reduce. It'll already be simple. Sum never reduces. Okay, so that's cool fact number one. Cool fact number two is if you double some prime number, and then you double some different prime number, and again, you pick numerators so that these fractions can't reduce. So this first comment is can't reduce based on numerator. Then in this case, it always reduces. Sum always reduces. Which is kind of cool. So this would be cool fact number two. And so we just kind of stumbled across this idea, but it took us forever to justify it. So we'll just try this one more time each, just to kind of get a feel for what the hell I'm talking about there. And I can come back to this if you want to write some more down. So let's just try it again. So I'm going to do the double version. So somebody give me a prime number.
19.
19. Okay. And doubling 19, what do we get? 38. And then a different prime number. Preferably something smaller.
7.
7, excellent. Doubling that, I get 14. Okay, now if I need to pick numerators so that these guys don't reduce, what kind of number do I have to pick? I got to pick an odd number because then, yeah, for sure. And then here it can't be 19, and here it can't be 7, right? Because that's 2 times 7, that's 2 times 19. So I got to pick some odd number. Like maybe here I'm going to pick 3, and maybe there I'm going to pick 5. Okay. So next thing to consider is let's use the LCD method here because we're trying to kind of think about whether it reduces or not, and the LCD method is key. So 38 came from 2 times 19. 14 came from 2 times 7. So what's the lowest common multiple here of those? Well, it's going to have to be 2 times 19 times 7. Anybody have a calculator handy? It's 2 times 19 times 7. 266. Thank you. So that's going to be our new denominator. But since everything's factored here, we can clearly see what do I need to multiply by the first fraction? What's it missing?
Oh.
Of those three factors?
Oh, 7.
It's missing the 7. Yeah, so that's the nice thing about having the factors all written out, the factors for each number and the factors for the LCM, because they can just look and say, oh, you're missing a 7, and this one is missing the 19. Okay, so 7 times, so underneath here I'll write the new fractions. So 7 times 3 is 21. And 5 times 19 is 95 maybe?
Yes.
Okay. And all of that is over 266. Because I have a common denominator, I engineered it. And so what's that give me? 90, 100, 110, 116?
Yes.
Over 266. And we can see if the numerator and denominator are both even, it's got to reduce. Half of 116 is 58, I think. And half of 266, I believe, is 133. And I'm mostly certain it won't reduce anymore. So can anyone see why this might always reduce the sum?
Doubling it would be multiplied by 2, so it should be divisible by 2.
So the denominator is guaranteed to be divisible by 2, yes. But why the new numerator? How come that one also ends up being divisible by 2? What did we have to pick for numerators here?
Odd numbers?
Odd numbers. Yeah. What are the missing factors on each side happen to be?
Odd numbers.
Odd numbers. And what happens when we add two odd numbers?
Even number.
You get an even number. Yeah. So because we're forcing the numerator, we started with odd numbers and then doubled them. And then we also started with odd numerators. And then we're forcing multiplications by other odd numbers. If you multiply two odd numbers, you get an odd number. But when you add two odd numbers, you get an even number. So it's always going to work out to be divisible by 2 in this case. And it's because we started with a pair of odd numbers that had nothing in common, and then we doubled them. And we picked numerators that had nothing in common with the denominator. So it's kind of a nice trick if you can remember that. Is it important to remember? No. But it's a cool little fact about fraction addition. When things reduce and when they don't, because it really is a tricky thing. Sometimes they happen to reduce, sometimes they don't. So the next question we were trying to answer is, if you randomly pick two fractions, what percent of the time will the answer reduce? And we think we know the percentage, but we can't prove it yet. It's on our list of things to do someday before we die. All right, so weird facts of addition. Let's back up and look at subtraction models, and then we'll play with our toys again. Subtraction. So we already have the fact that fractions are equal parts of a whole. The next thing we have to do is we have to decide, what does subtraction mean physically? So what do we have for options for physical meanings of subtraction?
Takeaway.
Takeaway is one. You remember any other ones? Subtracting isn't always taking away from something. What is it?
Comparing.
Compare is the other one, so that's the other option. Or compare. And depending on which one you go with, Is it ARE or AIR? AIR. And the pictures will look different depending on whether you go with takeaway or whether you go with compare. So let's start off with takeaway, so I'll switch back to blue. When you pick examples here, you want to pick them carefully so you don't actually end up with a negative number. So let's take 1/2, and we're going to subtract from that, say, 1/3. Oops. And the way I'm drawing it here is the comparison model. So excuse me. So I'm going to try and model 1/2 minus 1/3. So first thing we do is we start off with our half and cut that in either direction you want. You pick which one you want to keep. I'm going to keep this one here. And what I recommend doing next is to do the takeaway is, now I don't see a third in here to take away, so I have to engineer it somehow. And so I would cut it like I would a third cake. So I want to cut it the other way. Oops. So what happens there is that I now get common denominators. And so then we can work on shuffling things up. So what's the new version of a half here?
3/6.
It would be 3/6. And what would the new version of a third be? It would be 2/6. So then I just shuffle things around a little. So I'm going to redraw this. That one, and that one, that one. And so now I need to take away 2 of those 6. So maybe I'll take away that one, and I'll take away that one. So now I can see that leaves 1/6. So that's takeaway, because I got to pull stuff out to see what's left. And some people like to redraw that final picture, only showing the thing that's left. Some teachers think it's fine to just have those crossed out. So let's do it with comparison in mind next. Oops. So 1/2, take away 1/3. So to compare them, I have to draw them both. So I draw my half, and I draw my thirds, and then I shape them. So here's my half. And say this one over here is going to be my third. And another thing I'd recommend when you draw these pictures, mix it up as to which one you pick. Like, don't always pick the first one for the third. Pick the middle one sometimes, or pick the last one sometimes. Just to get kids to think a little more. So then, just like addition, I have to cut each cake like the other. So I cut half in thirds, I cut the third in half. So now I can see I have 3/6, take away 2/6, or compared to 2/6, excuse me. Person here. So when I compare them, I try to match them up. So So I could say, for example, these two pieces are alike, and then these two pieces are alike. And this piece right here is how they're different. So they differ by 1 out of those 6 pieces in the whole. Now, I tend to like the comparison model better. I think it's easier to work with drawing both fractions. I can instantly see what's going on. Gotta think harder on the takeaway one. Everyone's a little different. Questions on this one? Okay. So in the way these models are drawn, I just want to demonstrate off to the side here. We had 1/2 minus 1/3. And when we cut each cake like the other, the whole third cake had to be cut in half, as well as the shaded part. So I had to take 2 times 3 to get 6 pieces and 2 times 1 to get 2 shaded pieces. The half cake got cut in thirds, which means not only the whole got cut into thirds to get 6 pieces, but that one had to be cut in thirds too, so it has 3. And then ultimately we end up subtracting the numerators and keeping the new denominator. And so when you model it this way, you're essentially using the Arawa method. If you cut each of the cake like the other, and one cake was cut parallel to the ground, the other was cut perpendicular to the ground, which is kind of nice.
Does the arrow one work all the time?
Yep. Yeah, because the thing, it just doesn't find the lowest common denominator, it just gives you a quick denominator. Sometimes the lowest common denominator is the same as what the arrow says, so sometimes they line up. But for example, if I had 1/6 minus 1/3, the arrow algorithm would say use 18, whereas the LCD algorithm would say use 6. So then they differ sometimes. You'll still get the same answer in the end. It doesn't matter. I think the arrow algorithm is a safe alternative for people that really struggle with the complication of the LCD method, or it's a great way to introduce it because it comes naturally out of drawing these pictures. All right. All right, let's take a look at our activity. See if there's any questions. So I'm going to grab, let's see, we looked at page 1, got that started. We got page 2 started, and then there's the fraction strips that they talk about. So I'm guessing most of you don't have fraction strips because you don't have the workbook. So let me print those for you. Now, okay, so we can use those for that last page. And then on the second page, we were going to try and model with the toys and then see if we can sketch out some different solutions here. So let's do number 7 together. So if you've already done it, just get out your version. If you haven't done it, then we'll take a look at it together. So new page. I need a screenshot of the key. Other important thing is when you do this with students, always have that key somewhere visible for everyone to see. If it's not on their desk, somewhere up in the room displayed for everybody. And then we're going to do 1.5 plus 2/3. So 1 1/2 plus 2/3. And did I get the dot paper yet? I don't think I did. Fill this up for me, and then I'll get you guys some dot paper. Screenshots. Hopefully is enough. So on the top, there's dot paper. On the bottom, there's fraction strips. So grab a couple of dot papers, because we'll need them for the next activities too, 8 and 9, and then grab a fraction strip printout too. So first thing we want to do is draw each of these. So I'm going to attempt to draw 1.5. My dot paper is oriented different than the pictures up there, but that's okay. So let's see.
Oh, thank you.
1. And 1/2. And I want to combine that with 2/3. So I'll do some shading here. So if I put 2 6 together, I'll get 1/3. So I guess I could go 1, there's another, then 2. This hurts my brain every time. There, no, that's not right. There. There. Okay. So here's my, oops, wrong pen. 1.5. And then, let's see, 2 6, so here's 1/3. Here's my other 1/3. That looks reasonable. Outline it, maybe, oops. And red, 1/3, 2/3. Ooh, here's a trivia question. What shape do I get when I make a 1/3? When I put 2 of those 6 together, that makes a special shape. You see it probably every day when you're driving around and get gas. Chevron, yeah, that's called the chevron. Yeah, yeah. So those are chevrons. I thought that was a cool name, chevron. For years, I thought it was a gas station, but no, it's a mathematical shape. It's kind of cool. All right, so now we got to put these together. So we need kind of a common denominator to talk about them. So what should we use for the denominator here? Yeah, 6 ends up being the way to go. And so, so the next stage would be cutting these guys up. And so rather than redraw them, I'm just going to go back over in red and break them into their 6th components. So drawing in all of those rhombuses to the best of your artistic ability. Better at this some days than others. Yeah, so now we can look at this and say this has 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9, 6 there. And this one has 1, 2, 3, 4, 6 there. And so now we can combine them together. So all together, we're going to end up with 13, 6. Would be one way to look at it. What else should I do to finish this? Yeah, so that's a good question. Yeah, mixed number versus reducing. That's one reason I picked this problem. So the next thing I'm going to do is I'm going to try to pool all of this to try and see how many holes there are. So I know this is the shape of one hole, and I definitely have a hole. The question is, do I have enough stuff to fill another hole? And I can see 1, 2 more hexagons. So yeah, I have a second hole sitting there. So I'm going to draw that. And then I'm going to draw a third hole just to deal with the leftover for that mixed number. Oops, missing a dot there. Estimate. Close enough. All right, so when I regroup these things, so this is equal to, we have this and this, give me this region here. Oops, I wanted that to be blue. All right. Love magic pens, they're so much fun. All right, and then let's see, these two will give me another. And then we have that one piece in there. Oops. So it looks like we can also, wrong color again. We can also say this looks like it is equal to 1, 2, and a sixth when we regroup. So question, which is the better answer, 13, 6 or 2 and a sixth? Depends on what you're doing with the numbers, yeah. So some people might look at 13 over 6 and say, well, that's not reduced. Well, I claim it is, because is there a number that goes into both 13 and 6? No, so this is reduced. It just happens to be an improper fraction. And this one is just the mixed number version. And they're both great. They're just different ways to express the answer. They're both correct. So either this is the right answer or that is the right answer. We have two possible good answers here, depending on how you look at it. All right, so let's break away from the toys for a second, then we'll come back to them. Let's focus on mixed numbers some more. And we'll do a little mixed number arithmetic. So let's take 2 1/3 minus 1 1/2. Common way that this is dealt with is they get stacked. 2 1/3 minus 1 1/2. Okay, can we easily subtract here? So kids have done multiple digit subtraction, so they know start on the left and work their way to the right, right? It's the common algorithm for that. So 1/3 minus 1/2, what do I have to do first? So I have to find a common denominator. So we do some work and we figure out the common denominator is sixths. 2 goes into 6 3 times. So we have 3 6. And then 3 goes into 6 twice. So we have 2 6 there. Okay, so take 2 6 and subtract 3 6. They're silent. That's a problem, right? So what do we have to do when we can't take 2 minus 3?
You have to borrow.
You have to borrow. Okay, so we come over to the 2 here to borrow. And what do? We cross out that 2 and we put a 1 there, and then we come over here and do what? Would it be what? No, because that would mean we borrowed 10. What are we borrowing? Yeah, what are our pieces? Our pieces are 6 here. We're borrowing 6. We just borrowed a whole, and a whole here is 6 6. Ouch. And so we have to say 2 plus 6. So now I have 8 6 there. So now I can say, okay, 8 6 minus 3 6 is 8 minus 3 is 5, so I have 5 6. 1 minus 1 is 0, so that's going to be the answer. Personally, I think this is a painful process. Ouch. It's doable, but you have to really think hard about what's being borrowed. And the common thing is, because we're honestly, humans are machines, right? where we borrow. Oh yeah, I borrow 10, make that a 12. I do it half the time because it's just a default reactive. So it's doable, but I would suggest a different approach. So let's do it differently. So we're going to, again, take our 2 1/3, and we're going to subtract our, let's see if I have that right, minus 1 1/2. What I would suggest instead is don't use mixed numbers, use improper fractions. So the procedure for improper is coming down here, you multiply, and then you add up there. So 2 times 3 is 6 plus 1, so that's 7/3. 1 times 2 is 2, plus 1 is 3/2. Now if I wanted, I could use the arrow method. 3 times 2, my new denominator is 6. 2 times 7, I have a 14. 3 times 3 is a 9. Remind yourself you're subtracting. So once we start doing addition and subtraction, if you're using the arrow method, rewrite that subtraction up top. Otherwise, kids will be so used to the addition, they'll want to add those numbers. So 14 minus 9 is 5. So I've got 5, 6 as the answer. So I think improper is the easier way to go to do this. And just a reminder why. Consider this number right here. Tiffany, can you read me what I wrote in red right there?
2 1/3.
Yeah, it is literally 2 and 1/3. So technically, when I rewrite this problem, what's really going on is we have 2 and 1/3 minus 1 and 1/2. So it's way more complicated than mixed number form. So the kind of general rule I would recommend, although you will see this in all of your textbooks, they will teach kids to do that. And some of the class will be fine with it, remembering that you're borrowing whatever that denominator is, not tens anymore. But I think that the better rule for all of these is to calculate with improper fractions, not mixed numbers. It's almost impossible to do with division. It's very difficult to do with addition and subtraction, and it's really difficult to do with multiplication. So just improper fractions are good for communicating numbers. Sorry, I said that wrong. Rewind, take that back. Mixed numbers are good for communication. So for example, 2 1/3 miles. Improper fractions for calculations. So it's easier to calculate with 7/3 than it is with 2 1/3. But if I'm talking to somebody, I wouldn't say go drive 7/3 miles. I would say go drive 2 1/3 miles, something like that. Okay, so let's see. What else did I have on my list of fun things to play with? Arrow versus LCD, we did that. Improper versus mixed, we got that. Crazy cool facts. Oh, I promised we would do just a little bit of algebra. All right. Quit. So I'm just going to put up a couple of algebra-based fraction problems, just mostly to just think about our algorithms, LCD versus the arrow algorithm. So consider 3 over x plus 5 over y. what would that be equal to? Use any method you like. Anybody missing a highlighter here?
That's fine, sorry. I got a mess up here.
So since x and y are two different variables, the Arawa algorithm basically gives the same thing as the LCD. Common denominator is xy. So that means top and bottom of this one are multiplied by y. So I'll have a 3y in the top. Here, top and bottom could be multiplied by x. So I get a 5x in the top. And then x and y are different variables. I don't know what they are. So I can't clean it up anymore. And I also can't cancel anything either, because I can't factor anything out to cancel. Questions on that? Too bad? All right. Good?
Yeah, I was just wondering if, like, say y was 3y. You reduce it?
If that was a 3y down here, so good question. So let's just put it in there for fun. Actually, I gotta start over. So 3 over x plus 5 over 3y. So then the LCD would be 3y. And then cross multiplying up this way, I get 3y times 3 over 9y. 5x still there. And then when I add, I'm going to get 9y plus 5x over 3xy, sorry. And so just like up here, some people might be tempted to cancel those y's, but I can't. And the reason is I can rewrite this fraction right here. Both the, oops. When I write a fraction in this way with that big fraction bar, that says both the 3y and the 5x are being divided by xy, right? Which is like kind of the in-between step to get from the left side to the right side. Now here, in this individual fraction, I can cancel the y's, right? But is there a y up here to cancel with it? So the only time you can reduce is if you could factor something completely out of both parts. Then you can cancel or reduce with something on the bottom. But I can't. And putting that extra 3 here but not there, this 3 would go into the 9, but it doesn't have anything to do with the 5x, so nothing cancels still. So no reduction here either. And that's a really, really hard one to get used to once kids start getting into algebra. That desire to cancel stuff out, because it feels so good. Do you remember that in algebra? Isn't canceling stuff out so wonderful? It's wham, wham, it's gone. It's like the highlight of algebra class. All right, let's do one more. How about 2 over a squared b plus 3 over ab squared? Give that your best shot, and we'll compare notes. So there's my claim for what the LCM has to be for the denominators. about that and see if you believe it. So notice I'm going for the LCM rather than the Arawa algorithm here, because the denominators are more complicated. So that's what I believe the answer is here. So I'll walk through that in just a second, how I got that. So one nice thing about having variables here is my denominators are essentially factored. So when I'm trying to calculate the LCM here, the first denominator says you better have an a squared in the denominator and you better have a b in there. Okay. The second one says you better have an a. Do I have enough a's? I have plenty of a's, but it says you better have a b squared. Ooh, I'm not quite there, so I need to up that to a b squared. So that's why I think the LCM had to be a squared times b squared. So then what's the first denominator missing? A b, so I have to multiply b top and bottom. So that's going to give me my 2b right here. And then what's the second denominator missing? It's missing the a, so I have to multiply a top and bottom. And a times 3 is the same as 3 times a, so that's where I got that. And as far as adding them goes, I can add a to b, and I just get a plus b. So it's just 2b plus 3a, and I can't really clean that up, because a and b are two different things. It'd be apples and bananas. What happens if you take 2 bananas and add 3 apples? What do you got?
2 apples and 3 bananas.
Yeah, that's right. So I got. I can't clean it up. I can't say. I could say I have 5 pieces of. I could say I have 5 pieces of fruits, but that changes things, right? So, these aren't like terms, so I can't simplify it, but I can add them by putting an addition sign in between. And that's the best I can do. And then from here, nothing really cancels. Can you factor anything out of the numerator? No, there's a 2 here, but no 2 there. There's a b here, but no b there. 3 here, but no 3 there. A here, but no a there. So nothing factors. Since nothing factors out of the numerator, there's nothing to cancel in the bottom. So this is as good as it gets. That would be the answer here. Okay, so those were just kind of to push the idea of the LCD or the Arawa algorithm and when you can reduce and when you can't reduce. All right, so I'm done talking about addition and subtraction of fractions. So we can use the rest of the time to clean up activity stuff. And then I think since there's only like 10 more or 15 minutes of class, I'm not going to introduce multiplication yet, unless anyone's dying to do it. We'll wait a few days. Okay. We're pretty much on track where I was hoping we'd be. So.